Hey everyone, I mentioned in the last video that I'd show you the derivations of how we got to those equations last video for question number 3, and then never got around to it. So I'm going to quickly do it here for those of you that are interested. Again, you don't need to know how to do this, but some people find it useful to see how we got to the equations we did. So when I say questions have been simplified and rearranged, this is typically what I mean, because you'll have a couple of those equations, and I'll point them out to you if you want on your equation sheet, where technically they're redundant, but some equations are just reduced to make it a little easier for you to just be able to pull it directly from your equation sheet, or on occasion they'll be more specific to a certain system. So what I mean is having gravity in the equation instead of acceleration, yet the rest of the equation is the same. So I'm more than happy to point that out to you. Again, some people just enjoy seeing it this way. So as you might have noticed, I've already drawn them out to try to keep this to be a bit shorter of a video. You can always stop, pause, go back and try to hear again what I said, but I'll go a little bit quicker. So again, we're just going to look at these original projectile motion equations and then how they become the shortened, rearranged, and condensed equations, and why we can only use these two when one of the two points that we have don't have any velocity. So in the case of projectile motion, it's only when we go to the apex, or in free fall situations when we're starting with zero motion, so no velocity, maybe from a free fall drop, let's say. So those are the two situations. So let's take a look at what that looks like. So first up here, we have our first equation that we're starting with, okay, that we can reduce for. And the problem that we're kind of looking at here is it's asking about height. So we're looking at the change, or the height of something, an object, a ball, a person, whomever, whatever, and the change in the y-axis as far as its a displacement. Okay, so this would be the x range down here, or the x-axis, which is also known as the range, when it goes from here to here. But again, we're just interested with the y-axis here. We only want to know the maximum height that it gets to. So when that happens, our velocity starts large, whatever it initially starts as. So this is our vi over here. It gets bigger, but as the downward acceleration of gravity slows down our object, it's going to get slower and slower until at the apex, right up at the top center, velocity equals 0. So it's instantaneously 0 right at the peak, just before it changes direction, with accelerating starting back downward as gravity starts to beat the velocity upward. Okay. So again, our velocity final in the system is 0. So because of that, we can look back here at our equation now. We can see that we've zeroed out our final velocity here, so we can rewrite it to be this line here. And what we're ultimately trying to do is isolate, again, the change in vertical displacement, or delta y. So to do that, the first thing we're going to do is we're going to try to get rid of this by minusing that from both sides. So then we see that we move that over here, and that's what we got here, written in the black. And then our next move here is in the green. So we can treat 2 gravity, because it's multiplication, as one chunk, or one variable. So we'll divide both sides by 2 gravity, or 2g. So that's the move in the green, so we can get rid of that now. And when we rewrite that, this is what we get. And this is your equation that you have on your sheet. So again, it's just a way to do all of this work for you so that you don't need to. Okay. Again, last kind of reminder, or I'll say it again, probably a few times, is this can only be used in a system where one of the two velocities, typically the final velocity, is 0. Okay, And you can flip your system as you need, but ultimately this is the easiest one: projectile motion to the apex, or a free fall drop. Those are two great examples of when you can use that here. Okay, great. Next example, similar idea, slightly different system. So in this problem, what we're trying to figure out in this projectile motion is at the very top of the apex. Again, yes, velocity is 0 again. It always is at the apex of projectile motion. But we want to figure out time. How long does it take for this change in displacement to occur? So for that, all we need to know is we can use this equation, okay? So to start working through it, again, final velocity is 0, so we can get rid of that like we did here. Our next step is to move the initial velocity over to the 0 side. So we can cross that out. That gives us this line here. Then we do our green move marked here. So again, delta t, or the change in time, is separate from gravity. So we take gravity, divide both sides by gravity, which means we can cross it off from this side. And here is the equation we end up with. Okay. Again, a simplified version of what we started off with, but it saves you all this time when you're on an exam. Okay.